Welcome to 3.1 Systems of Equations and Inequalities Review. Yes, this should be review from Algebra 1, but we are going over the topic so that you can have a refresher. These notes are kind of long, so I do suggest you only write down important information. You don't necessarily have to write down every single step and instruction that I do. So let's get started. The first thing we're going to do is determine the number of solutions for each system of equations below. The important thing here is going to be slope and y-intercept. So we're going to get these equations to look as similar to each other as possible. So for number 1, I'm going to multiply the bottom equation by 3 for every single term. So that's going to give me 3x plus 7y equals 22. And if you notice, now my equation looks exactly the same as the one that's at the top. So it has the same slope and the same y-intercept. So when I graph these two lines, they are the exact same line. So they will intersect at every single point on the line. This is just an example of what it could look like. So this is going to have infinite solutions. For number 2, I'm going to go ahead and divide everything in the bottom equation by 2, which is going to give me y plus 5 over 2x equals negative 4. And if I want it to look like the top equation, I have to subtract 5 over 2x from both sides. And if you notice now, if I compare this equation to my equation on the top, they have the same slope but a different y-intercept. Now, anytime you have two equations with the same slope but a different y-intercept, they are parallel. So these two lines are never going to intersect, meaning they are never going to have a solution. This is a no solution problem. For number 3, our third case, if the infinite solutions is not occurring and no solution is not occurring, we have two equations with a different slope. Now, anytime your slope is different, you are going to only have one solution. They're only going to intersect in one place. Moving on to tables and graphs. For tables, you are interested in where you have the same x and y value for both equations. Now, tables are normally presented to you in this manner, where you have one x column and you have one column for your first equation and one column for your second equation. So y1 and y2 are going to be using the same x values. So you're interested in where the y values are the same. So I have 2 and 4, not the same. 1/2 and negative 7 over 2, not the same. Negative 5 over 2 and negative 5 over 2, I like that. And negative 7 and negative 1, not the same. So my solution is going to be 3/2 negative 5 over 2. So one thing you can do when you are given a table problem is just completely ignore the equations. You don't need them. Yes, you could technically solve them using the equations, but it will save you so much more time to just look at the table. The solution to table problems will always be written as a coordinate point. So make sure that you don't just highlight the line where they are the same x and y value, you actually write the coordinate point. For number 5, we are going to graph a system of linear equations. So the first thing I always suggest doing is make it look like an equation you can understand. So we want these to be y equal problems. So I'm going to go ahead and add x to both sides of my first equation, which is going to give me y equals 3x. And then I'm going to divide everything in my second equation by negative 1, which is going to give me y equals x minus 2. I'm going to have my little curly bracket signifying a system. Now, I do want to do a quick refresher for graphing lines. We have y equals mx plus b. This is the form you are most used to seeing. M is going to represent slope, so rise over run, and b is going to be your y-intercept. So I'm going to graph my first equation. I don't have a y-intercept for this one, so it's going to cross at the origin, 0, 0. So I'm going to plot my y-intercept first. So it's going to be at 0. And then from here, I'm going to do the slope. So my slope is 3. We treat that as 3 over 1. So I'm going to rise 3, 1, 2, 3, run 1. Do the same thing again, 1, 2, 3, run 1. And then you're going to go in the opposite direction, 1, 2, 3 over 1, 1, 2, 3 over 1. And then you can connect your dots so that you have your linear graph. For my second equation, I'm going to do the same thing. The only difference is now I have a y-intercept of -2. So my first point is going to be at -2, and then my slope is 1. So I'm going to rise 1, run 1, rise 1, run 1, and do the same thing in the opposite direction, and draw my two connecting lines. Once I've done this, I am interested in finding the intersection of these two lines, which I can see is clearly here. So my solution to this problem is going to be the coordinate point -1, -3. And yes, you do have to write it as a coordinate point. Now we're going to use substitution to solve each system. So I do include instructions here. You do not have to write them down if it is something you are comfortable with. Our first step is going to be to solve one equation for y or x. Now, in our system, I already have a singular y, so that's what I'm going to solve for. So I added 9x to both sides of the equation, which is going to give me y equals 9x plus 1. My next step is going to be plugging into the other equation. So I'm going to take this equation, y equals, and plug it in everywhere that I see a y. So now I have 2/3 x plus 1/3, 9x plus 1 equals 2. Then we are going to solve for the variable. So the only variable I have in this equation is x now, which is the goal. So I'm going to go ahead and solve. I distributed the 1/3. 1/3 times 9 is 3, and 1/3 times 1 is 1/3. Now I'm going to multiply everything through by 3 because I personally would rather not deal with fractions, which is going to give me 2x plus 9x plus 1 equals 6. Going to combine like terms. I get 11x equals 5, which is x equals 5 over 11. Once you've found one value, all you have to do is plug that back in to solve for the other variable. So I use the equation that I created by adding 9x to both sides. Y equals 9 times 5 over 11 plus 1. So I first multiplied 9 times 5 to get 45 over 11. And I rewrote 1 as 11 over 11 because that's the same thing. 11 over 11 reduces to be 1. When I add these two things together, I get 56/11. Now, always we are going to write our answer as a coordinate point. 5 over 11, 56 over 11. Now, this question is a little tricky. It does not necessarily want the solution. We want y minus x. So I went ahead and did 56 over 11 minus 5 over 11 is 51 over 11. Make sure you pay attention to the question and you are answering it completely. For number 7, I'm going to do something similar. I'm going to solve for a variable. So here I believe I subtracted 2 from each side, giving me y equals -3x minus 2. And then I'm going to substitute this -3x minus 2 everywhere I see a y in my first equation. So I have 3x plus -3x minus 2 equals 3. Going to simplify this 3x and this -3x cancel each other out, and I end up with -2 equals 3. Well, that's not quite true. Actually, it's very, very false. And when you end up with a false statement, you have no solution. This is something that does occur. So anytime you have a statement at the end that is not true, you're always going to say no solution. Now to move on to elimination. So I do have a note for elimination. The goal is to eliminate one variable at the beginning, and then you're going to want the coefficients to be the same value with opposite signs in order to do this. So when I look at my x's and my y's, you could technically eliminate either one. It really is what you choose. I'm going to go ahead and eliminate the x's. So I know that 3 and 2, the next number that they will have in common is 6. So I want one to be a positive 6 and one to be a negative 6. So let's deal with our first equation first. I multiplied the first equation by 3 for every single term, which gave me 6x plus 12y equals negative 30. Now, since this is the positive one, my second equation has to be the negative one. So I'm going to multiply everything in the second equation by negative 2, which is going to give me negative 6x minus 6y equals 6. So elimination then has you add both of these equations together. That's why it's called linear combination, because we're going to add them linearly. So 6x minus 6x ends up to be 0x. 12y minus 6y is 6y. And negative 30 plus 6 is negative 24. From here, you're just going to solve for the other variable. So I have divided by 6, y equals negative 4. Once you have one variable, you're going to do the same thing we did with substitution. You're going to substitute that value in order to solve for the other variable. So I'm just going to plug negative 4 in. You could choose either equation. You're going to get the same answer. 2x plus 4 times negative 4 is equal to negative 10. Going to solve, and I end up with x equals 3. Now, for a general solving problem, you're going to want to write your answer as a coordinate point, 3, negative 4. But for this particular problem, and when I multiply y times x, I get 3 times negative 4 is negative 12. This would be my answer for this problem. For number 9, I'm going to follow a similar method. I already have negative 6 here, and I know I can multiply 3 by 2 to get positive 6. So I'm not even going to change the second equation. I'm going to go ahead and multiply the top equation by 2, which is going to give me 6x minus 4y equals 10. And then I'm going to combine linearly. Negative 6x plus 6x is 0x. 4y minus 4y is 0y. And negative 10 plus 10 is 0. So we ended up with a statement that said 0 equals 0. Well, that's true. And when something is true and we don't necessarily have a solution, meaning we don't get an x value and a y value, we have a situation where we end up with infinite solutions. Um, it does not have to be 0 equals 0. It could be 5 equals 5. It could be 10 equals 10 or 2 equals 2. As long as it is a true statement, you will have infinite solutions. Now let's talk about solving systems of inequalities by graphing. So some key information. You are going to treat these as if they are linear equations. M is going to be your slope, B is going to be your y-intercept. The only difference is this equal to sign is going to be replaced by an inequality. And it's going to tell us a couple of things. First, whether we're going to have a solid line if the equal to is there, or a dashed line if it's not. I will always recommend that you have y isolated on the left-hand side, because then you can easily determine if you're shading above if it's greater or below if it's less than, because you will have to determine where the direction of the shading goes. Next, let's talk about solutions to systems of inequalities. In order to be a solution, it has to satisfy every inequality in the system. So the shaded area where you have an overlap is where your solutions are going to lie. Now, the borders of that shaded area also contain solutions if it is a solid line. So notice that the point that is lying on the solid line border is a solution, but the point that is lying on a dotted border is not a solution. So if I were to have a point right here at the intersection of these two lines, because it is laying on a dashed line, it cannot be a solution. So it would not be considered one. And anything outside of the double shaded area is definitely not a solution. So let's look at our graph. We are going to write a system of inequalities for the graph below. We're going to identify one point that is a solution and one point that is not a solution. So first, you have to write your equations. My suggestion is to always identify your y-intercept first. So I'm going to work with this dashed line to begin with. So my y-intercept is right here at 1. So I have a y-intercept of 1. And then you're going to want to identify some pretty points so that you can figure out what the slope is. So my next pretty point that I see is right here at 1, -1. So I can tell my line is going down 2 over 1. So a rise of -2, a run of 1. So my slope is going to be -2. So to write my equation, I'm going to have y, and technically if this were an equation, it would be an equals to 2x plus 1, but I have to decide what inequality is going to go here. First, I know it's a dashed line, meaning it's not going to be an equal to. But if I pay attention to where the shading is, everything below the dashed line is being shaded. So remember, if y is isolated on the left, which mine is, if I'm shading below the line, it should be less than symbols. And we've said it's just a less than, not a less than or equal to. So I have y is less than 2x plus 1. Now for my second equation, I'm going to go again and identify my y-intercept. My y-intercept is -2. I'm going to identify another pretty point, and my rise is 1, my run is 3, so my slope is going to be 1/3. I always kind of write out my inequality as an equation first with my y isolated on the left. And I notice that everything above the line is shaded in. So if I'm shading above the line and it's solid, it's going to be greater than or equal to. And here is my system for this graph. Now, I do just need to identify one point that is a solution and one point that is not a solution. You could really pick anything. I believe I picked, let's see, -4, 1. It's in the double shaded region, and 5, -3. Definitely outside of any shaded region. Any points that fell on this solid border would have been considered solutions. None of these points on the dashed border or the intersection would be a solution. Let's write two variable systems. So it's almost time for candy sales. You know what I mean. I can buy a 2-pound bag of Skittles for $3.99 and a 1-pound bag of Nerds for $1.99. I ended up with 10 pounds of candy. This is going to be my weight equation, and spent $19.93. This is going to be my money equation. If my niece can guess the exact amount of candy I bought, she can have dessert before dinner. Create a system of equations that she could use so she can have dessert before dinner. So the first thing you're always going to want to do is define your variables. So I said let x be the number of bags of Skittles, let y be the number of bags of Nerds. So I'm going to have two equations. I'm going to have one for weight and one for money. So I'm going to say, since the Skittle bags are 2 pounds, 2x is going to represent the weight of Skittles. And since the Nerds bags are 1 pound, 1x is going to represent the weight of Nerds. So when I write this equation, I'm going to end up with 2x plus 1y is going to have to equal to 10. Now for money, all you have to do is write a similar equation, but instead of 2, I'm going to plug in 399. And instead of 1, I'm going to plug in 199 because 399 times the number of Skittles plus 199 times the number of nerds is going to total out to be 1993. So all you have to do is write the equation. You do not have to solve it. For number 12, we are going to create a garden in our backyard. At Home Depot, the cost of Miracle Grow soil is $7.97 each, and veggie seeds cost $1.99 per bag. We want to plant at least 3 different veggies. We don't want to spend more than $50. Write a system of linear inequalities that we could use to find all the possible ways we can spend our money. So again, we are going to first define our variables. I let X be the number of bags of Miracle Grow and Y be the number of bags of veggie seeds. And I'm going to deal with the fact that I want at least 3 different veggies first. So I'm going to have a equation or an inequality, where y has something to do with 3. And we want it to be at least 3. So y needs to be greater than or equal to 3. And we don't want to spend more than $50. So I need to deal with money. So $7.97 times the number of bags of Miracle Grow and $1.99 times the number of bags of veggie seeds cannot be more than $50. So I have 797x plus 199y has to be less than or equal to 50.